Hi everyone, welcome back to Medicine Academia. So please don't forget to like our videos, so share so that others can be able to benefit from this tutorial. So another thing, we are still into for another episode. Here we're going to talk about chemical kinetics. As I mentioned earlier, all the reagents aspect is there in the materials. So if you subscribe, you'll be able to have an access to our materials. I will base on only calculation aspect so that you'll be able to save time and save hours too as well. So you don't need to worry anything. We are not the best. We are just trying to be the best. You understand? You know, you cannot be the best. You're just trying to give you the best. So now today we talk about chemical kinetics. Chemical kinetics. This one. Kinetics. So I will only base on rate law. Based only on rate law, according to what we have material and how to find the half-life equations. So the rate law here is always dealing with what we have at the product side, at the reactant side rather. It's always dealing with what we have at the what? At the reactant side. So for the said, the rate law is a mathematical expression which relates the rate of reaction to the constitution of the reactant raised to some powers. So what are they trying to say? Let's say for a reaction like this, let's say I have X. Let's say we have product. So if I want to apply the rate law here, I just have rate law is equal to constant. You can see the first one is A. Can you see? We normally base on what we have at the reactant side. That is A raised to the power of X. And the second one is B raised to the power of Y. Can you see that? Rate law is equal to constant A raised to the power of its mole. It is X. B raised to the power of its mole. It's just as simple like that. Once you ask to find the rate law, this is the way we normally find the rate law. So let's see some example. They say find the rate law of the following. We have to find the following. We have to write the rate law of the following reactions. N2O5 So I was asked to write the rate law for this. 2 hydrogen gas plus hydrogen gas, 2 hydrogen iodide. The third one, so look at the first one. We are asked to write the others for this. How are we going to write that? You know, I told you anything you are writing for the rate law is based on what we have at the reactant. So the rate law for this, look at it, it's very simple and straightforward. That's going to be constant. What do we have at the reactant? You can see this is what we have at the reactant. There's only one value that we have there. So we have N2O5 raised to the power of 2. Can you see that? Rate law is equal to constant. N2O5 then raised to the power of what? Raised to the power of the mole that we have. If I want to do the second one, let's see the second one. If I want to write the rate law for the second one here, the rate law for the second one here is going to be constant. You can see what we have there is 2, not like this one. You know, this one is not separate, but here is separate. That's hydrogen gas. That's for the first one. So you know what we have there is 1. It's not 2. 2 is subscript, so power of 1. Then hydrogen gas is to the power of 1 as well. So the addition of all this, after we find the rate law, the addition is what we call order. It can be order 2, order. Let me just discuss about the order 2 as well. When we are asked to calculate order of a reaction, is after we find its rate law, we can be able to determine its order. Like for example, if I was asked to determine the order of this one, what is going to be the order? It's going to be order 2 because the power is 2, right? So if I was asked to find the order of this one, additions, because this one is 2, to find the order of this, I can say order of this one is going to be, the first one is 1, The second one too is also 1. So 1 plus 1, of course, we are going to have 2. So that means this one is of order what is order 2. So even if I want to do this, it's going to be based on what we have at the reactant side. So that's going to be NO2 raised to the power of 2. Of course, the order is going to be what? It's going to be 2 as well. I hope you are following, right? Good. Let's look at this. They said you should determine the order of this one. They have already calculated its rate. They say rate is equal to constant CHL3 flowing gas half. So I was asked to determine the order of this one. So how will I do that? You can see the power of this one is 1 and this one is half. So down here we have 1 plus 1 over 2. So this is SM is 2. This is 2 plus 1. This is 3 over 2. That is 1 number 1 over 2. So then the order is 1 half. So the addition of, after we find the rate law, is what we call order. So we also have another one, classification of order of reactions. We can have first order, as I mentioned. We can have unimolecular order. We can have bimolecular. It's the molecularity of this, or we can have 3. Okay. Classification of order of reactions. We have classification of order of reactions. Classification of order of reactions. There, it's just after you find the rate law, you determine its order. So we have a name. If this one, we call it unimolecularity. If this one, unimolecularity. If it is 2, we call it bi. We call it bimolecularity. If it is 3, we call it thermolecularity. If it is 2, molecularity, we can call it bimolecular. So 2, then for 3, we call it thermolecular. It's 3. Just like after you determine the order, for example, let me give you a clear example of that. Let's say I have CH3, COO, C2H5 plus H2O gives CH3 COOH plus C2H5OH. You see this one? So if I want to determine the what do we call it? If I want to determine the molecularity of this, let's firstly find its rate law of X. As usual, rate law based on what we have at the reactant. So here I can have K. So what I have here is a CH3 COOH C2 C2H5. That's the first one. Raised to the power of 1, because the power we have there is 1. Then the second one is H2O raised to the power of 1 as well. So if I want to determine the order, if I want to determine the order will be when we add the power together, right? So the power of the first one is 1, the second one too is 1, so 1 plus 1, and we have 2. So if you are also determine the type of classification of this one is going to be by molecularity. Molecular. So just like addition of the powers of the order that we have after finding the order. So that's what we have for this case. Then they put another one. They put how to find the half-life of a order of reactions. How to find the half-life. You can see that it's simple, right? Yeah, it's very simple and straightforward. So this one is talking about the half-life, just like related to the activity, the activity we have what we call half-life. So How can we find the half-life for a first order reaction? Half-life for a first order reaction. It's still the same thing as the one you know in radioactivity. The half-life of that is always given as 0.693 over lambda. Some people can use lambda, some can use K. Where use K, we call it a decay constant. Some people can use K, don't mind that. They can use lambda or they can use K. Anyone they use, either they use lambda here or they use K, is still talking about the same thing, which is a decay constant. So for example, they said, let's look at this one. They say compound A decomposes to form B, and C, the reaction is first order. The reaction is first order at 25 degrees Celsius. And we can also call it another thing, we can call it rate constant. So still the same thing. The rate constant for the reaction is 0.450 per second. What is the half-life? What is the half-life? Of A at 25 degrees Celsius. So you just have to just pick out the data. Compound A decomposed to form B, and C, the reaction is first order. At 25 degrees Celsius, the rate constant as our K is given as 0.450 per second. Then now say we should find the half-life. Just simple and straightforward. Just a simple substitution. So according to what we have, half-life is equal to 0.693 over K over lambda. So now, down here I can have 0.693 divided by, what we have for K is 0.450. So let's divide that and see the result. We have 0.693 divided by 0.450. So if I divide that, what I have here is 1.54. 1.54 seconds. So in some cases, you'll be asked to find your K2, just make it. For example, if I was asked to find the K, maybe I'll be given the half-life. If I was asked to find the K constant, I will just make it as a subject, you know. If I come multiply, I can have K T half-life is equal to 0.693. So now, by making the K as the subject, the value will start by T half-life, half-life. So this cancels this, then I can have K to be equal to 0.693 over time. So that's what we have for this case. You can see that it's very simple. How to determine the rate law is simple. How to determine the order, and how to classify it, and how to find the half-life of the first order reaction. So please don't forget to like our videos, shares. If you are enjoying us, just trying to share. We are not the best, we're just trying our best. So kindly watch the videos, subscribe to our channel, share so that other too can be able to benefit. This is Medicine Academia. We're just trying our best. Thanks for watching.